1. Newtonian mechanics. Newtonian mechanics is the foundation of classical physics, describing how objects move under the influence of forces. Developed by Isaac Newton in the 17th century, it provides a framework for understanding motion in everyday life, from falling apples to planetary orbits. The core idea is that objects remain at rest or in uniform motion unless acted upon by an external force. The relationship between force, mass, and acceleration determines how objects respond to influences like gravity, friction, and applied forces. This framework allows for precise predictions of motion, making it essential for engineering, transportation, and space exploration. Newtonian mechanics also introduces the concept of action and reaction, where every force exerted on an object results in an equal and opposite force. It applies to macroscopic objects but begins to break down at very high speeds, near light conditions, or at atomic scales, where relativity and quantum mechanics become necessary. Despite these limitations, Newtonian mechanics remains one of the most useful and widely applied theories in physics, forming the basis for fields like structural engineering, ballistics, and celestial mechanics. It provides a deterministic view of the universe, where given enough information, one can precisely calculate future positions and velocities of objects. 2. Classical thermodynamics. Classical thermodynamics studies the relationships between heat, work, and energy in physical systems. It is based on 4 fundamental laws that govern how energy is transferred and transformed. The first law states that energy cannot be created or destroyed, only converted between different forms, such as from heat to mechanical work. The second law introduces the concept of entropy, a measure of disorder, which always increases in a closed system, explaining why heat flows from hot to cold objects and why perpetual motion machines are impossible. The third law states that as a system approaches absolute zero, its entropy approaches a minimum, making it impossible to reach absolute zero. The 0th law defines temperature by establishing that if 2 systems are in thermal equilibrium with a third system, they are in equilibrium with each other. Classical thermodynamics is crucial in engineering, chemistry, and astrophysics, helping design engines, refrigerators, and power plants. It also explains why energy efficiency is limited and why some processes are irreversible. Although classical thermodynamics does not consider the microscopic behavior of atoms, its macroscopic laws remain universally valid, providing deep insights into the natural tendency of systems to evolve toward equilibrium. 3. Electromagnetism. Electromagnetism describes the interaction between electric and magnetic fields, forming the basis of modern electrical technology. It explains how charged particles produce electric fields and how moving charges generate magnetic fields. This theory unifies electricity and magnetism, showing that they are 2 aspects of the same fundamental force. The interaction between electric and magnetic fields enables the propagation of electromagnetic waves, including visible light, radio waves, and X-rays. These waves do not require a medium to travel, allowing them to move through the vacuum of space. Electromagnetism is essential for understanding electrical circuits, motors, generators, and communication systems. It governs the behavior of electrons in atoms, influencing chemistry and material science. The study of electromagnetism led to the development of Maxwell's equations, which describe how electric and magnetic fields evolve and interact. These equations paved the way for technological advances such as wireless communication, radar, and lasers. Electromagnetic forces are vastly stronger than gravitational forces at the atomic level, making them responsible for the structure of matter and chemical bonds. This field is crucial in both classical and modern physics, bridging the gap between fundamental forces and practical applications in daily life and industry. 4. Special relativity. Special relativity, developed by Albert Einstein in 1905, revolutionized the understanding of space and time by showing that they are not absolute, but interwoven into a single entity called spacetime. It introduced the concept that the laws of physics remain the same for all observers moving at constant velocity, regardless of their frame of reference. One of its most striking consequences is time dilation, where time slows down for objects moving close to the speed of light relative to an observer. Another key effect is length contraction, meaning that objects in motion appear shorter along the direction of travel. The theory also established that mass and energy are interchangeable, leading to the famous equation that shows how a small amount of mass can be converted into a tremendous amount of energy. This principle underlies nuclear reactions and explains the immense energy output of stars. Unlike Newtonian mechanics, which assumes that time and space are fixed, special relativity demonstrates that simultaneity is relative, meaning that two events occurring at the same time for one observer may happen at different times for another. This theory is essential for modern physics, influencing technologies like GPS, particle accelerators, and the study of cosmic rays. 5. Basic quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales, where classical physics fails to apply. It reveals that particles such as electrons and photons exhibit both wave-like and particle-like properties depending on how they are observed. This fundamental duality is illustrated by the double-slit experiment, where particles behave like waves when not measured, but appear as individual particles when observed. Quantum mechanics also introduces the concept of superposition, meaning that a particle can exist in multiple states simultaneously until measured. Another key principle is quantum entanglement, where two or more particles become correlated in such a way that measuring one instantly affects the state of the other, regardless of distance. The uncertainty principle states that certain properties, like position and momentum, cannot be known with absolute precision at the same time. Quantum mechanics has led to groundbreaking technologies, including semiconductors, lasers, and quantum computing. It also provides the foundation for understanding atomic and molecular structures, chemical bonding, and the behavior of subatomic particles. Despite its success in explaining microscopic phenomena, quantum mechanics challenges classical intuitions, raising philosophical questions about the nature of reality and the role of the observer in physical measurements. 6. General relativity, pop science version. General relativity, formulated by Albert Einstein in 1915, is a theory of gravity that replaces Newton's concept of a force acting at a distance. Instead, it describes gravity as the curvature of spacetime caused by mass and energy. According to this theory, massive objects like planets and stars bend the fabric of spacetime, influencing the motion of other objects around them. This explains why planets orbit the sun and why light can be bent by strong gravitational fields, a phenomenon known as gravitational lensing. One of the most famous predictions of general relativity is the existence of black holes, regions where gravity is so intense that nothing, not even light, can escape. The theory also predicts gravitational waves, ripples in spacetime caused by accelerating massive objects, which have been detected by observatories on Earth. Unlike Newtonian gravity, which works well for weak fields and low speeds, general relativity becomes necessary for understanding extreme environments such as neutron stars, black holes, and the expansion of the universe. It has practical applications in technologies like GPS, which must account for time dilation effects caused by Earth's gravity. General relativity remains one of the most successful and experimentally verified theories in modern physics. 7. Standard model basics. The Standard Model of particle physics is a theoretical framework that describes the fundamental particles and forces governing the universe, except for gravity. It classifies all known particles into two main groups: fermions, which make up matter, and bosons, which mediate forces. Fermions include quarks and leptons, with quarks combining to form protons and neutrons, while leptons include electrons and neutrinos. The forces between these particles are carried by bosons: the photon for electromagnetism, the W and Z bosons for the weak nuclear force, and the gluon for the strong nuclear force. The Higgs boson, discovered in 2012, is responsible for giving particles mass through the Higgs field. The Standard Model successfully explains a wide range of physical phenomena, from the behavior of atoms to the interactions in particle accelerators. However, it has limitations, as it does not incorporate gravity, dark matter, or dark energy. Scientists continue searching for a more complete theory, possibly through extensions like supersymmetry or grand unified theories. Despite its shortcomings, the Standard Model remains one of the most rigorously tested theories in physics, with experiments at the Large Hadron Collider continuing to refine its predictions. 8. Nuclear physics. Nuclear physics studies the structure, behavior, and interactions of atomic nuclei, which consist of protons and neutrons bound together by the strong nuclear force. It explains phenomena such as radioactivity, nuclear fission, and nuclear fusion. In fission, a heavy nucleus splits into smaller nuclei, releasing energy, a process used in nuclear power plants and atomic bombs. Fusion, on the other hand, occurs when light nuclei combine to form a heavier nucleus, releasing even more energy, as seen in stars like the Sun. Nuclear physics also describes radioactive decay, where unstable nuclei emit particles and energy over time, leading to applications in medicine, archaeology, and energy production. It is fundamental to understanding isotopes, elements with the same number of protons but different numbers of neutrons, which are used in radiocarbon dating and nuclear medicine. The field has practical applications in nuclear reactors, medical imaging, and radiation therapy. Despite its benefits, nuclear physics also raises challenges, including nuclear waste management and the risks associated with nuclear weapons. Research continues into harnessing nuclear fusion as a potential source of limitless clean energy, with projects like ITER aiming to replicate the conditions inside the Sun to produce sustainable power on Earth. 9. Lagrangian and Hamiltonian mechanics. Lagrangian and Hamiltonian mechanics are advanced reformulations of classical mechanics that provide deeper insights into motion and energy. These approaches go beyond Newtonian mechanics by using mathematical principles to describe the behavior of physical systems in a more generalized and elegant way. Lagrangian mechanics, developed by Joseph Louis Lagrange, focuses on the concept of energy rather than forces. It expresses the motion of a system using a function that represents the difference between kinetic and potential energy. By applying a principle known as the least action, Lagrangian mechanics determines the path a system will take naturally, making it highly effective in analyzing complex systems such as planetary motion, fluid dynamics, and electromagnetism. Hamiltonian mechanics, developed by William Rowan Hamilton, further refines this approach by transforming the equations of motion into a system of equations that describe how a system evolves over time. Instead of focusing on velocity, as in Lagrangian mechanics, it introduces a new function that represents the total energy of a system, split into kinetic and potential components. This method is particularly useful in quantum mechanics, statistical mechanics, and chaos theory, as it allows for a deeper understanding of conserved quantities, symmetries, and long-term system behavior. Both Lagrangian and Hamiltonian mechanics provide powerful tools for solving problems that are difficult to handle using Newton's laws alone. These methods are widely used in theoretical physics, celestial mechanics, and modern engineering. They also serve as a bridge between classical and quantum physics, as the principles underlying quantum mechanics are built upon the mathematical foundations of Hamiltonian mechanics. Despite being more abstract than Newtonian mechanics, these formulations offer a more universal perspective on physical laws, enabling physicists to describe motion in curved spaces, complex dynamical systems, and even relativistic and quantum phenomena. 10. Quantum field theory, QFT, basics. Quantum field theory, QFT, is the fundamental framework that describes the behavior of elementary particles and their interactions. Unlike traditional quantum mechanics, which treats particles as individual entities, QFT represents them as excitations of underlying fields that permeate all of space. Each type of particle, such as electrons, quarks, and photons, corresponds to a specific quantum field. These fields constantly fluctuate due to quantum uncertainty, allowing for the spontaneous creation and annihilation of virtual particles. One of the core ideas in QFT is that forces arise from the exchange of force-carrying particles called gauge bosons. For example, the electromagnetic force is mediated by photons, while the strong nuclear force is carried by gluons. This concept of force mediation explains how particles interact over distances without direct contact. Feynman diagrams provide a visual representation of these interactions, depicting how particles exchange energy and momentum through virtual particles. QFT successfully unifies quantum mechanics with special relativity, making it the most accurate description of nature at the subatomic level. It forms the foundation of the Standard Model, which describes all known fundamental particles and forces except gravity. One of its major successes was predicting the existence of the Higgs boson, which was later confirmed through experiments at the Large Hadron Collider. However, QFT also faces challenges, particularly in integrating gravity into its framework, leading to ongoing research in quantum gravity and string theory. Beyond particle physics, QFT has applications in condensed matter physics, where it helps explain phenomena like superconductivity and phase transitions. Despite its complexity, QFT remains one of the most powerful tools in modern physics, allowing scientists to predict experimental results with extraordinary precision and advancing the understanding of the universe's fundamental structure. 11. Cosmology. Cosmology is the scientific study of the origin, evolution, structure, and ultimate fate of the universe. It seeks to understand the large-scale properties of the cosmos, including the distribution of galaxies, the nature of dark matter and dark energy, and the fundamental laws governing space-time. Modern cosmology is based on the Big Bang theory, which proposes that the universe began as an extremely hot and dense singularity approximately 13.8 billion years ago before expanding and cooling into its current state. Observations of the cosmic microwave background radiation provide strong evidence for this theory, showing the faint afterglow of the early universe just 380,000 years after the Big Bang. One of the major discoveries in cosmology is the accelerating expansion of the universe, attributed to dark energy, a mysterious force that counteracts gravity on cosmic scales. Additionally, dark matter, an invisible substance that does not emit or absorb light, is believed to make up most of the universe's mass, influencing galaxy formation and motion. The large-scale structure of the universe, consisting of galaxy clusters, superclusters, and vast cosmic voids, provides insight into how matter has evolved under the influence of gravity over billions of years. Cosmology also explores fundamental questions about the nature of time, space, and the possibility of a multiverse. Various theoretical models suggest that our universe may be just one of many, each with different physical laws and properties. The study of black holes, cosmic inflation, and quantum fluctuations in the early universe continues to shape our understanding of reality. With advancements in observational tools like space telescopes and gravitational wave detectors, cosmology remains one of the most dynamic fields in modern physics, pushing the boundaries of human knowledge about the universe and its ultimate destiny. 12. Statistical mechanics. Statistical mechanics is a branch of physics that connects the microscopic behavior of individual particles with the macroscopic properties of matter. It provides a statistical framework for understanding how large systems of atoms and molecules behave collectively, explaining concepts like temperature, pressure, and entropy. Unlike classical mechanics, which describes individual particles with precise trajectories, statistical mechanics deals with probabilities and averages, recognizing that tracking every particle in a system is impractical. One of the key ideas in statistical mechanics is the concept of the partition function, which encodes all possible states of a system and determines its thermodynamic properties. By analyzing how particles distribute their energy, statistical mechanics explains why systems naturally evolve toward equilibrium, where macroscopic properties become stable. This principle underlies the second law of thermodynamics, which states that entropy or disorder tends to increase in an isolated system. Statistical mechanics successfully describes phase transitions, such as the melting of ice or the boiling of water, by modeling how particle interactions change at different energy levels. It also plays a crucial role in understanding gases, liquids, and solids, as well as more complex phenomena like superconductivity and magnetism. In addition to classical applications, statistical mechanics provides the foundation for quantum statistics, distinguishing between bosons, which can occupy the same state, and fermions, which obey the Pauli exclusion principle. This distinction explains the behavior of photons in lasers, electrons in metals, and even the stability of atomic structures. Beyond physics, statistical mechanics has applications in fields like biology, economics, and information theory, where it helps model complex systems with many interacting components. Despite its probabilistic nature, it offers deep insights into why macroscopic physical laws emerge from microscopic chaos, making it one of the most powerful tools in theoretical physics. 13. Superconductivity and superfluidity. Superconductivity and superfluidity are quantum phenomena that occur at extremely low temperatures, revealing exotic states of matter where conventional physical laws break down. Superconductivity is the ability of certain materials to conduct electricity with zero resistance, meaning an electric current can flow indefinitely without losing energy. This effect occurs when electrons form Cooper pairs, moving through the atomic lattice without scattering. Superconductors expel magnetic fields, a property known as the Meissner effect, which allows them to levitate magnets and has applications in technologies like MRI machines, maglev trains, and quantum computing. While conventional superconductors require near absolute zero temperatures, high-temperature superconductors, discovered in the 1980s, function at more practical levels but remain a subject of intense research. Superfluidity, on the other hand, is a state of matter in which a liquid flows without viscosity. This means it can pass through tiny pores without resistance and even climb up the walls of its container. Helium-4 becomes a superfluid at extremely low temperatures, forming quantum vortices that defy classical fluid dynamics. Unlike normal liquids, superfluids exhibit macroscopic quantum behavior, where all particles move in a single coherent state. This property makes them useful for studying quantum turbulence and rotational effects in astrophysical objects like neutron stars. Both superconductivity and superfluidity arise from quantum mechanical principles, particularly Bose-Einstein condensation and collective particle behavior. They demonstrate how macroscopic quantum effects can manifest in everyday materials under the right conditions. These discoveries have profound implications for condensed matter physics, leading to developments in quantum materials, ultra-cold atomic research, and the quest for room-temperature superconductors, which could revolutionize energy transmission and technological efficiency in the future. 14. Plasma physics. Plasma physics is the study of the fourth state of matter, where atoms are ionized, meaning electrons are stripped from their nuclei, creating a mixture of free electrons and ions. Unlike solids, liquids, or gases, plasma behaves uniquely due to its ability to conduct electricity and respond to magnetic fields. Plasmas are the most abundant form of matter in the universe, making up stars, lightning, and even the interstellar medium. They can be classified into different types, such as thermal and non-thermal plasmas, depending on how energy is distributed among the particles. One of the key features of plasma is its collective behavior, meaning that electric and magnetic fields strongly influence particle motion. Unlike neutral gases, plasmas support waves and instabilities, leading to phenomena such as magnetic reconnection, which is responsible for solar flares and auroras. Plasmas also play a critical role in astrophysics, governing the dynamics of accretion disks around black holes, solar winds, and the behavior of intergalactic plasma clouds. Plasma physics has significant technological applications, particularly in nuclear fusion research. Fusion, the process that powers the sun, involves combining light atomic nuclei to release vast amounts of energy. Scientists aim to replicate this process in reactors like tokamaks and stellarators, where high-temperature plasmas are confined by powerful magnetic fields. Success in this area could provide a nearly limitless and clean energy source. Additionally, plasmas are used in industry for plasma cutting, semiconductor fabrication, and plasma propulsion systems for spacecraft. Despite its complexity, plasma physics remains one of the most dynamic fields in modern science, bridging astrophysics, energy research, and advanced materials science. Understanding how to control plasmas is key to unlocking future technologies, from sustainable energy to space exploration. 15. Black hole. Thermodynamics. Black hole thermodynamics is a branch of theoretical physics that applies the principles of thermodynamics to black holes, revealing deep connections between gravity, quantum mechanics, and information theory. Traditionally, black holes were thought to be simple objects defined only by their mass, charge, and angular momentum. However, in the 1970s, Stephen Hawking and Jacob Bekenstein showed that black holes also possess entropy, suggesting they follow thermodynamic laws. One of the key discoveries in black hole thermodynamics is that black holes emit radiation, now known as Hawking radiation. This challenges the classical notion that nothing can escape from a black hole. Due to quantum effects near the event horizon, particle-antiparticle pairs can form, with one falling into the black hole and the other escaping, leading to a slow loss of mass. Over immense timescales, this process causes black holes to evaporate completely. Black holes obey the four laws of black hole thermodynamics, which resemble the classical laws of thermodynamics. The area of a black hole's event horizon behaves like entropy, meaning that it can only increase or stay constant, similar to the second law of thermodynamics. This has profound implications for the nature of information in physics, leading to the black hole information paradox, which questions whether information falling into a black hole is permanently lost or preserved in some way. The study of black hole thermodynamics is crucial for understanding the relationship between gravity and quantum mechanics. It has influenced ideas in quantum gravity, holography, and the search for a theory of everything. Insights from this field continue to shape modern physics, particularly in string theory and the study of spacetime's fundamental structure. 16. Neutrino physics. Neutrino physics studies one of the most elusive and mysterious fundamental particles in the universe. Neutrinos are nearly massless, electrically neutral particles that interact only through the weak nuclear force and gravity, making them incredibly difficult to detect. They are produced in vast quantities during nuclear reactions, such as those occurring in the Sun, supernovae, and nuclear reactors. Despite being one of the most abundant particles in the universe, neutrinos pass through matter almost unaffected, with trillions of them streaming through the Earth and our bodies every second without any noticeable interaction. One of the biggest discoveries in neutrino physics is that neutrinos oscillate between different types, or flavors, as they travel. This means they have a small but non-zero mass, contradicting early predictions from the standard model of particle physics. This discovery, confirmed through experiments in the late 20th and early 21st centuries, led to significant revisions in particle physics and earned researchers the Nobel Prize in Physics. The study of neutrino oscillations provides critical insights into physics beyond the standard model, potentially offering clues to the nature of dark matter and the asymmetry between matter and antimatter in the universe. Neutrinos also play a key role in astrophysics and cosmology. They help scientists understand the processes inside stars, including supernovae, where neutrinos carry away most of the explosion's energy. Detecting neutrinos from distant cosmic events allows astrophysicists to study extreme environments that are otherwise inaccessible. Underground neutrino detectors, such as Super Kamiokande in Japan and IceCube in Antarctica, are designed to capture rare neutrino interactions, shedding light on their properties and potential new physics. As research continues, neutrino physics remains one of the most promising fields for uncovering hidden aspects of the universe and testing the limits of our understanding of fundamental particles. 17. Gauge theory and Yang-Mills equations. Gauge theory is a fundamental framework in modern physics that describes the forces of nature using symmetry principles. It is the mathematical foundation of the Standard Model, explaining how elementary particles interact through fundamental forces. At its core, gauge theory is based on the idea that certain physical laws remain unchanged under local transformations, meaning that nature possesses inherent symmetries that dictate particle behavior. These symmetries give rise to force-carrying particles, or gauge bosons, which mediate interactions between matter particles. One of the most important developments in gauge theory is the Yang-Mills equations, formulated in the 1950s by Chen-Ning Yang and Robert Mills. These equations generalize electromagnetism to describe the strong and weak nuclear forces. Unlike classical electromagnetism, where the photon mediates the electromagnetic force, Yang-Mills theory introduces more complex interactions involving non-abelian symmetries, meaning that force carriers can interact with each other. This concept is essential for understanding the strong nuclear force, which binds quarks together inside protons and neutrons through the exchange of gluons. Gauge theory successfully unifies three of the four fundamental forces: electromagnetism, the weak force, and the strong force, under the Standard Model. However, gravity remains an outlier, as attempts to describe it within a gauge theory framework have not yet been fully successful. The search for a quantum theory of gravity, possibly involving gauge principles, is one of the biggest challenges in modern physics. Beyond particle physics, gauge theory has applications in condensed matter physics, explaining superconductivity and topological phases of matter. It also plays a crucial role in string theory and quantum gravity research. The mathematical richness of gauge theory has even influenced pure mathematics, leading to breakthroughs in geometry and topology. Its deep connection to nature's fundamental forces makes it one of the most powerful and far-reaching ideas in theoretical physics. 18. Supersymmetry, SUSY. Supersymmetry, or SUSY, is a theoretical extension of the Standard Model that proposes a deep symmetry between matter and force-carrying particles. In the Standard Model, matter is made up of fermions, such as electrons and quarks, while forces are mediated by bosons, such as photons and gluons. Supersymmetry suggests that every fermion has a corresponding bosonic partner, and vice versa. These hypothetical partner particles are called superpartners, with names like selectrons for electrons, squarks for quarks, and gluinos for gluons. One of the main motivations for supersymmetry is that it solves several problems in particle physics. First, it provides a natural explanation for why the Higgs boson is much lighter than expected. Without SUSY, quantum corrections should make the Higgs mass incredibly large, but supersymmetry cancels these corrections, stabilizing its value. Second, SUSY helps unify the fundamental forces at extremely high energies, suggesting that the strong, weak, and electromagnetic forces were once a single force in the early universe. This supports the idea of grand unified theories, GUTS. Another major implication of supersymmetry is that it offers a candidate for dark matter. The lightest supersymmetric particle, LSP, often assumed to be a neutralino, could be stable and interact weakly, making it a perfect explanation for the mysterious dark matter that accounts for most of the universe's mass. Despite its theoretical appeal, supersymmetry has not yet been confirmed experimentally. Searches at the Large Hadron Collider have not found evidence of superpartners, leading some physicists to question whether SUSY exists or if it operates at energies beyond current detection limits. Nevertheless, the idea remains influential in high-energy physics, quantum gravity research, and string theory, as it provides one of the most compelling extensions of our understanding of fundamental particles and forces. 19. String theory and M-theory. String theory is a theoretical framework that seeks to unify all fundamental forces of nature, including gravity, by proposing that the basic building blocks of the universe are not point-like particles, but tiny, vibrating strings. The different modes of vibration of these strings correspond to the various particles observed in nature. Unlike the Standard Model, which treats gravity separately from the other forces, string theory naturally incorporates gravity by predicting the existence of a massless spin-2 particle, identified as the graviton. This makes it one of the leading candidates for a theory of everything. One of the key features of string theory is that it requires extra dimensions beyond the familiar 3 of space and 1 of time. In most versions, string theory predicts a total of 10 or 11 dimensions, with the extra ones being compactified at scales too small to be observed directly. These additional dimensions allow for the possibility of multiple universes, or the multiverse, where different regions of reality may have entirely different physical laws. M-theory is an extension of string theory that emerged in the 1990s and suggests that the 5 different versions of string theory are actually different perspectives of a single, deeper theory. M-theory requires an 11-dimensional universe and introduces higher-dimensional objects called branes, which could explain why gravity appears weaker than the other fundamental forces. According to this framework, our universe may exist as a 3-dimensional brane floating in a higher dimensional space, with gravity leaking into extra dimensions. Despite its mathematical elegance, string theory lacks direct experimental evidence. No experiments have yet confirmed the existence of extra dimensions or supersymmetric particles predicted by the theory. Critics argue that string theory is more of a mathematical construct than a physical theory, but it remains one of the most active areas of research in theoretical physics, offering deep insights into black holes, quantum gravity, and the fundamental nature of reality. 20. Quantum gravity. Quantum gravity is the theoretical field that seeks to reconcile the principles of quantum mechanics with general relativity, creating a unified description of gravity at the smallest scales. In general relativity, gravity is explained as the curvature of spacetime caused by massive objects, while quantum mechanics governs the behavior of particles and forces at subatomic scales. However, these two theories are fundamentally incompatible because general relativity describes gravity as a smooth, continuous fabric, whereas quantum mechanics suggests that space and time should have discrete, quantized properties at extremely small scales. One of the main challenges of quantum gravity is the problem of singularities, such as those inside black holes and at the Big Bang. At these points, space-time curvature becomes infinite, meaning that classical physics breaks down, and a quantum theory of gravity is needed to describe what happens. Several competing approaches attempt to solve this problem. One of the leading candidates is string theory, which suggests that gravity arises from the vibrations of tiny strings rather than being a fundamental force. Another major approach is loop quantum gravity, which proposes that spacetime itself is made up of discrete loops, forming a quantum structure rather than a continuous fabric. Quantum gravity also introduces fascinating ideas, such as the holographic principle, which suggests that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This idea has been used to explain black hole entropy and Hawking radiation, offering insights into how information might be preserved rather than lost when matter falls into a black hole. Although quantum gravity remains one of the biggest unsolved problems in physics, progress is being made through indirect experiments, such as studies of black holes, cosmic microwave background fluctuations, and high-energy particle collisions. A successful quantum gravity theory would revolutionize our understanding of the universe and could potentially lead to new insights into the fundamental nature of space, time, and reality itself. 21. ADS-CFT correspondence. The ADS-CFT correspondence, also known as the holographic principle, is a revolutionary idea in theoretical physics that suggests a deep connection between gravity and quantum field theory. Proposed by Juan Maldacena in 1997, it states that a gravitational theory in a higher dimensional space, anti-de Sitter space, or ADS, is mathematically equivalent to a conformal field theory, CFT, defined on its lower dimensional boundary. This means that a universe with gravity can be fully described by a theory without gravity on its surface, providing a new way to understand quantum gravity and black holes. One of the most striking implications of ADS-CFT is its ability to explain the quantum nature of black holes. In this framework, a black hole in the bulk ADS space corresponds to a thermal system in the boundary CFT, offering a new perspective on Hawking radiation and black hole entropy. It also provides insights into the black hole information paradox, suggesting that information falling into a black hole is not lost, but encoded in the lower dimensional boundary theory. Beyond black holes, ADS-CFT has applications in high-energy physics, condensed matter physics, and even nuclear physics. It has been used to describe strongly coupled quantum systems, such as quark-gluon plasmas produced in heavy ion collisions. The correspondence also plays a crucial role in the search for a quantum theory of gravity, as it provides one of the most concrete realizations of holography, where a higher dimensional universe emerges from a lower dimensional theory. Despite its success in theoretical research, ADS-CFT is primarily a mathematical tool and has not yet been confirmed experimentally. Moreover, our universe does not exhibit anti-de Sitter geometry, but rather a de Sitter structure due to cosmic expansion, However, the principles behind ADS-CFT continue to inspire new ideas in physics, potentially leading to deeper connections between spacetime, information, and quantum mechanics. 22. Renormalization in QFT. Renormalization is a fundamental technique in quantum field theory, QFT, used to deal with infinite quantities that arise when calculating particle interactions. In QFT, particles interact by exchanging virtual particles, and these interactions involve summing over all possible energy levels, including extremely high energies. This often leads to divergent, infinite results for physical quantities like mass and charge, making the theory seemingly non-physical. Renormalization systematically removes these infinities by redefining physical parameters in a way that keeps predictions finite and measurable. The key idea behind renormalization is that observable quantities, such as the charge of an electron or the strength of a force, depend on the energy scale at which they are measured. At high energies, quantum fluctuations become more significant, modifying the effective charge and mass of particles. By introducing a cutoff scale, physicists can absorb infinities into redefined parameters, ensuring that the final results match experimental observations. This process allows theories like quantum electrodynamics, QED, and quantum chromodynamics, QCD, to make precise predictions, such as the magnetic moment of the electron, which agrees with experiments to astonishing accuracy. Renormalization also provides deep insights into the behavior of physical systems at different energy scales. The renormalization group, developed by Kenneth Wilson, describes how physical constants evolve as the energy scale changes. This approach is crucial in understanding phase transitions, such as in condensed matter physics, where it explains critical phenomena like superconductivity and magnetism. Despite its success, renormalization remains a challenge in quantum gravity, where traditional techniques fail to remove infinities. This has led to alternative approaches, such as string theory and loop quantum gravity, which attempt to resolve these issues by modifying the structure of spacetime at the smallest scales. Renormalization remains one of the most powerful tools in modern physics, providing a framework for understanding the deep connections between quantum theory, field interactions, and the nature of fundamental forces. 23. Quantum chromodynamics, QCD. Quantum chromodynamics, QCD, is the branch of quantum field theory that describes the strong nuclear force, which binds quarks together to form protons, neutrons, and other hadrons. Unlike electromagnetism, where charged particles interact by exchanging photons, QCD introduces a new type of charge called color charge, which comes in three varieties: red, green, and blue. The force between quarks is mediated by massless particles called gluons, which themselves carry color charge, allowing them to interact with each other, unlike photons in electromagnetism. One of the defining properties of QCD is asymptotic freedom, meaning that at extremely high energies or short distances, quarks behave as if they are free and barely interact. However, at larger distances, the force between quarks grows stronger, preventing them from being isolated. This leads to color confinement, the phenomenon where quarks are permanently bound inside protons and neutrons, never observed as free particles. If energy is supplied to try to separate quarks, new quark-antiquark pairs are created instead, leading to the formation of more hadrons. QCD explains the structure of atomic nuclei and plays a crucial role in high-energy physics experiments, such as those conducted at the Large Hadron Collider. It also describes the behavior of quark-gluon plasma, a state of matter thought to have existed in the early universe just after the Big Bang, where quarks and gluons were not confined into hadrons. This plasma has been recreated in particle collisions, providing insight into the early moments of the universe. Despite its success, QCD is notoriously difficult to solve analytically due to the complexity of strong interactions. Instead, numerical simulations using lattice QCD techniques are used to approximate solutions. The study of QCD remains a major area of research, with implications for understanding fundamental particles, neutron stars, and the deeper structure of matter itself. 24. Axions and dark sector particles. Axions and dark sector particles are hypothetical entities proposed to solve some of the biggest mysteries in physics, including the strong CP problem and the nature of dark matter. Axions were first theorized in the 1970s as a solution to why the strong nuclear force does not violate charge parity CP symmetry, even though other interactions, such as the weak force, do. According to quantum chromodynamics, QCD, CP violation should naturally occur in strong interactions, yet experiments show no such effect. The introduction of the axion provides a mechanism that cancels this violation, making it a compelling candidate for new physics. One of the most intriguing aspects of axions is that they could also explain dark matter, the invisible substance that makes up most of the universe's mass, but does not interact via electromagnetism. If axions exist, they would be extremely light, electrically neutral, and interact weakly with ordinary matter, making them difficult to detect. However, they could still influence astrophysical and cosmological processes, such as cooling rates of stars and the formation of galactic structures. Experiments like ADMX, Axion Dark Matter Experiment, and CASPER are actively searching for signs of axions by detecting their potential conversion into photons in strong magnetic fields. Beyond axions, the concept of a dark sector refers to a set of yet undiscovered particles that interact through forces beyond the standard model. These could include dark photons, sterile neutrinos, or other exotic particles that only interact weakly with known forces. Dark sector particles might mediate interactions between dark matter and regular matter, providing a new way to detect and understand the hidden mass of the universe. The search for axions and dark sector particles is one of the most active frontiers in modern physics, with potential discoveries reshaping our understanding of both fundamental forces and the unseen components of the cosmos. 25 tachyons. Tachyons are hypothetical particles that, if they exist, would travel faster than the speed of light. Unlike ordinary particles which require infinite energy to reach the speed of light according to special relativity, tachyons are theorized to always move faster than light and would require infinite energy to slow down to subluminal speeds. This unusual property places them outside the realm of conventional physics and has led to significant debate about their implications. One of the major consequences of tachyons is their potential violation of causality. In special relativity, faster-than-light travel could allow for signals to be sent backward in time, leading to paradoxes such as the possibility of altering past events. This challenges the fundamental structure of spacetime and suggests that if tachyons exist, they might not interact in a way that allows for direct causal violations. Some interpretations suggest that tachyonic fields might only result in instabilities, rather than real superluminal particles. Tachyons first appeared in theoretical physics in the context of quantum field theory, where certain fields exhibited imaginary mass values, leading to instabilities. These tachyonic instabilities do not necessarily imply actual faster-than-light particles, but instead suggest that a system is in an unstable state and will transition to a lower-energy, stable configuration. In string theory, tachyons arise in early versions of the theory, but are interpreted as signals of an unstable vacuum, requiring the system to undergo spontaneous symmetry breaking. Despite their intriguing properties, no experimental evidence for tachyons has ever been found. Their existence remains speculative. and most modern theories treat them as mathematical artifacts rather than real particles. However, their study continues to provide insights into the boundaries of relativity, quantum field theory, and possible new physics beyond our current understanding. 26. Negative mass and exotic matter. Negative mass is a hypothetical concept in physics where an object would have mass with a negative value, leading to bizarre and counterintuitive behavior. Unlike normal matter, which accelerates in the direction of an applied force, negative mass would accelerate in the opposite direction. This property could create strange effects, such as self-propelling motion, where a negative mass object, when pushed, moves toward the force instead of away from it. The idea of negative mass arises in various theoretical contexts, including solutions to Einstein's general relativity equations. Some exotic solutions, such as the Alcubierre warp drive, require negative mass or negative energy density to create spacetime distortions that could allow faster-than-light travel. Another example is the hypothetical existence of wormholes, which, according to theory, would require exotic matter with negative energy to remain stable and traversable. In quantum physics, negative energy states appear in certain cases, such as in the Casimir effect, where vacuum fluctuations create a region with lower than normal energy. This has led to speculation that quantum effects might allow for the creation of small regions of negative energy, though large-scale negative mass objects have never been observed. Some theories also propose that dark energy, the mysterious force driving the accelerated expansion of the universe, could be related to exotic negative energy properties. Despite its theoretical appeal, negative mass remains purely speculative, with no experimental evidence supporting its existence. If it were discovered, it could revolutionize physics, leading to groundbreaking advancements in space travel, gravitational manipulation, and the fundamental understanding of space-time. However, its strange properties also challenge conventional physics, making it one of the most intriguing and controversial topics in modern theoretical research. 27. White holes. White holes are hypothetical cosmic objects that are the theoretical opposites of black holes. While black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape, white holes are regions where nothing can enter, and matter and energy can only be ejected. According to general relativity, white holes would behave like time-reversed black holes, continuously expelling matter and radiation while remaining completely inaccessible from the outside. The concept of white holes first emerged as a mathematical consequence of the equations describing black holes, particularly in solutions like the Schwarzschild metric. In some interpretations, white holes are thought to be connected to black holes via wormholes, forming a bridge between different regions of spacetime or even different universes. This idea suggests that material falling into a black hole could, in theory, be expelled from a white hole in another part of the cosmos, though no observational evidence supports this. White holes have never been observed, and their physical existence remains speculative. Some theories propose that white holes might be extremely short-lived, forming as quantum fluctuations in spacetime and then quickly disappearing. Others suggest that the universe itself might have originated from a massive white hole explosion, similar to the Big Bang. Certain astrophysical phenomena, such as unexplained high-energy gamma-ray bursts, have been proposed as possible signatures of white holes, but no conclusive evidence has been found. Despite their speculative nature, white holes remain an interesting possibility in theoretical physics, particularly in the context of quantum gravity and black hole information paradox solutions. If they exist, they could provide profound insights into the nature of spacetime, the conservation of information, and the ultimate fate of matter falling into black holes. 28. Causal fermion systems. Causal fermion systems are a mathematical framework that aims to unify quantum mechanics, general relativity, and quantum field theory into a single, coherent theory of fundamental physics. Unlike traditional approaches, which rely on continuous spacetime as a background structure, causal fermion systems propose that spacetime itself emerges from more fundamental quantum entities. In this theory, the fundamental building blocks of reality are not particles or fields, but rather objects called causal fermions, which encode both matter and the structure of spacetime. One of the key insights of causal fermion systems is that the geometry of spacetime arises from an underlying variational principle, meaning that the fundamental laws of physics result from an optimization process. This differs from general relativity, where spacetime curvature is determined by the energy and momentum of matter. The theory suggests that both quantum mechanics and gravity emerge naturally from the interactions of causal fermions, potentially providing a route toward a theory of quantum gravity. Causal fermion systems also offer a new way to understand non-locality, a phenomenon where quantum effects seem to influence distant objects instantaneously. Unlike standard quantum mechanics, which struggles to reconcile non-local interactions with relativity, this approach treats non-locality as a fundamental aspect of reality built into the structure of causal relations. While still in the early stages of development, causal fermion systems present a promising alternative to more established quantum gravity approaches, like string theory and loop quantum gravity. If proven correct, this framework could fundamentally change our understanding of spacetime, providing a deeper, more unified description of reality that integrates all known forces and particles into a single mathematical structure. However, experimental tests for this theory remain challenging, and its predictions need further exploration to determine whether they align with physical observations. 29. Wormholes and traversable. Spacetime wormholes are hypothetical shortcuts through spacetime that could connect distant regions of the universe or even different universes. First proposed as a solution to Einstein's equations of general relativity, they are often described as tunnels with two ends, allowing for nearly instantaneous travel between vastly separated points. These structures are sometimes referred to as Einstein-Rosen bridges, named after Albert Einstein and Nathan Rosen, who first introduced the concept in 1935. For a wormhole to remain open and stable, it would require exotic matter with negative energy density. In classical physics, gravity always attracts, but negative energy could create a repulsive effect that prevents the wormhole from collapsing. Some quantum field theories suggest that negative energy could exist in small amounts, such as in the Casimir effect, but whether it can be harnessed to sustain a traversable wormhole remains uncertain. Theoretical models, such as the Morris-Thorne wormhole, describe a scenario where advanced civilizations or future technology could use exotic matter to create stable, human-sized wormholes. If traversable wormholes exist, they could revolutionize space travel, allowing for interstellar or even intergalactic journeys without violating the speed of light. Some theories also propose that wormholes could enable time travel, as differences in gravitational time dilation between the two ends might allow for movement backward or forward in time. However, this raises questions about causality and paradoxes, such as the grandfather paradox, where traveling to the past could alter events in a way that prevents the traveler from ever making the journey. Despite their theoretical appeal, no observational evidence for wormholes has been found. Some astrophysical anomalies, such as certain black hole behaviors, have been speculated to involve wormholes, but no definitive proof exists. The search for wormholes continues in both theoretical physics and astrophysical observations, as their discovery would fundamentally change our understanding of space, time, and the limits of human exploration. 30. Simulation hypothesis. The simulation hypothesis proposes that reality as we perceive it might be an artificial construct similar to a highly advanced computer simulation. This idea, popularized by philosopher Nick Bostrom in 2003, suggests that if a civilization advances far enough technologically, it could create highly detailed simulations indistinguishable from reality. If such simulations are possible, and civilizations are likely to create many of them, then statistically, it becomes more probable that we are living in a simulation rather than in the base reality. One of the strongest arguments supporting the simulation hypothesis is the rapid advancement of computing power and artificial intelligence. Modern video games and virtual reality already provide increasingly realistic simulations, and if technology continues to progress exponentially, future civilizations might develop simulations so detailed that conscious beings inside them would not be able to distinguish them from real life. Additionally, some physicists argue that certain aspects of quantum mechanics, such as wave function collapse and quantum entanglement, could be interpreted as evidence of underlying computational processes. The idea that the universe is pixelated at the Planck scale, with a finite limit to resolution, further aligns with the concept of a digital simulation. Critics argue that there is no empirical evidence supporting the hypothesis and that it is largely speculative. They point out that while it is theoretically possible for advanced civilizations to create simulations, there is no way to determine if we are inside one. Some also suggest that if we were in a simulation, observable glitches or inconsistencies in physical laws might occasionally appear, though none have been conclusively identified. Despite the lack of direct evidence, the simulation hypothesis remains a fascinating thought experiment, influencing both philosophy and physics. It raises deep questions about the nature of consciousness, the fundamental limits of knowledge, and whether we can ever truly understand the reality in which we exist. If proven true, it would challenge everything we assume about existence, identity, and the nature of the universe itself. 31. Retrocausality. Retrocausality is the idea that effects in the present or future can influence events in the past, challenging the conventional understanding of cause and effect. In classical physics, causality is strictly one-directional. Causes precede effects, and time flows forward. However, in certain interpretations of quantum mechanics, retrocausality appears as a possibility, suggesting that information or influences might travel backward in time under specific conditions. One of the main areas where retrocausality is discussed is in quantum entanglement. In experiments involving entangled particles, measuring the state of one particle instantaneously determines the state of the other, regardless of distance. Some interpretations propose that the measurement retroactively determines the particle's properties at the moment of entanglement, implying that future actions influence past events. This perspective is still debated, as most physicists interpret quantum entanglement through non-locality rather than retrocausal effects. Another area where retrocausality emerges is in Wheeler's delayed choice experiment. In this setup, a decision made after a photon has already entered an experimental apparatus appears to retroactively determine whether it behaved as a wave or a particle in the past. Some researchers argue that this suggests a form of retrocausality where future measurements influence past states of a system. However, others maintain that this is a misinterpretation and that quantum mechanics does not require backward-in-time influences. If retrocausality were real, it would have profound implications for our understanding of time, free will, and information transfer. It could theoretically allow for paradoxes, such as sending messages to the past, though no experiment has demonstrated such an effect in a way that allows for practical time travel. While retrocausality remains speculative, it continues to intrigue physicists and philosophers, pushing the boundaries of what we know about time and the nature of reality. 32. Mathematical universe hypothesis. The mathematical universe hypothesis, proposed by physicist Max Tegmark, suggests that the fundamental nature of reality is purely mathematical. According to this idea, the universe is not merely described by mathematics, but is itself a mathematical structure. This means that all physical phenomena, from the smallest subatomic particles to the largest galaxies, are emergent properties of mathematical relationships rather than existing within a separate physical space. One of the key arguments for this hypothesis is the extraordinary effectiveness of mathematics in describing physical laws. From Newton's laws of motion to Einstein's equations of general relativity and the intricate symmetries of quantum mechanics, the universe appears to follow mathematical rules with remarkable precision. If every aspect of reality can be expressed mathematically, then it raises the question of whether reality itself is fundamentally mathematical, rather than just governed by mathematical principles. The hypothesis also suggests that all possible mathematical structures exist as physical realities in different forms. This implies that other universes governed by entirely different mathematical laws could exist in a broader multiverse of mathematical possibilities. In this framework, the reason we perceive certain mathematical laws in our universe is not due to any special physical cause, but because we happen to inhabit a mathematically self-consistent structure that allows for the emergence of intelligent observers. Critics argue that the mathematical universe hypothesis is more of a philosophical idea than a testable scientific theory. Since it does not yet make unique, falsifiable predictions, it remains speculative. However, it offers a radical perspective on the nature of existence, suggesting that mathematics is not merely a tool for understanding reality, but is reality itself. If proven correct, this hypothesis would redefine our understanding of the universe, consciousness, and the very nature of being. 33. Consciousness and quantum mechanics. The relationship between consciousness and quantum mechanics is one of the most debated and mysterious topics in physics and philosophy. Some interpretations of quantum mechanics suggest that the act of observation plays a fundamental role in shaping reality, leading to speculation that consciousness itself may influence physical processes. This idea is often linked to the famous measurement problem, where a quantum system exists in a superposition of states until it is observed, at which point it collapses into a definite state. One of the most well-known interpretations supporting a connection between consciousness and quantum mechanics is the von Neumann-Wigner interpretation, which proposes that the observer's consciousness causes the collapse of the wave function. In this view, reality remains in a probabilistic quantum state until a conscious being perceives it, suggesting a direct link between mind and matter. This interpretation has been criticized for lacking experimental evidence, and most physicists prefer explanations that do not require consciousness to play a fundamental role. Another idea, orchestrated objective reduction, OR, was proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that quantum processes inside microtubules in the brain may be responsible for human consciousness. This theory attempts to bridge quantum mechanics and neurobiology, proposing that consciousness arises from quantum computations in biological structures. However, this hypothesis is highly controversial, as the brain is a warm, noisy environment where quantum coherence is unlikely to be sustained for long periods. While quantum mechanics undeniably plays a role in the fundamental workings of nature, there is no widely accepted scientific evidence that directly links it to consciousness. Most physicists view consciousness as an emergent property of classical neural processes rather than a quantum phenomenon. However, the question remains open, and future discoveries in quantum biology or neuroscience may provide new insights into the possible connections between the mind and the quantum world. 34. Hyperdimensional physics. Hyperdimensional physics explores the idea that reality consists of more than the familiar three spatial dimensions and one time dimension. The concept originates from both theoretical physics and speculative metaphysics, suggesting that additional dimensions may exist beyond human perception. While everyday experience is limited to three-dimensional space, several advanced physical theories require extra dimensions to explain fundamental forces and particle interactions. One of the most well-known frameworks incorporating higher dimensions is string theory, which suggests that elementary particles are not point-like objects, but rather vibrating strings that exist in a 10 or 11-dimensional spacetime. In this model, the extra dimensions are compactified, or curled up at scales too small to be observed directly. These hidden dimensions could provide explanations for fundamental physical properties, such as why gravity is much weaker than the other fundamental forces. The Randall-Sundrum model proposes that our universe might be a lower-dimensional brane embedded in a higher-dimensional space, with gravity leaking into extra dimensions, offering a possible explanation for dark matter or dark energy. Beyond theoretical physics, some speculative ideas suggest that higher dimensions could play a role in consciousness, parallel universes, or even time travel. Some interpretations of hyperspace theories propose that advanced civilizations might access higher dimensions to manipulate spacetime, enabling faster-than-light travel or wormhole creation. Although extra dimensions have not been directly observed, experiments such as those conducted at the Large Hadron Collider, LHC, continue searching for evidence, such as the presence of higher dimensional effects in particle collisions. If confirmed, hyperdimensional physics would revolutionize our understanding of the universe, revealing a reality far richer and more complex than previously imagined. Until then, the existence of higher dimensions remains one of the most intriguing possibilities in modern physics. 35. Anthropic principle. The anthropic principle is the idea that the fundamental constants and physical laws of the universe appear fine-tuned to allow for the existence of life, particularly intelligent observers like humans. This principle attempts to explain why the universe has precisely the right conditions for galaxies, stars, planets, and life to exist, rather than a chaotic or sterile cosmos. There are two main versions of the anthropic principle: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle states that we observe a universe with conditions suitable for life simply because we exist in such a universe. If conditions were different, we wouldn't be here to ask the question. This is considered a tautology rather than an explanation. The strong anthropic principle, on the other hand, suggests that the universe must have fundamental laws that inevitably give rise to life, implying a deeper reason for the fine-tuning of physical constants. Some scientists and philosophers argue that the anthropic principle supports the multiverse hypothesis, which proposes that our universe is just one of many, each with different physical constants. In this view, we exist in a universe where the conditions for life are met simply because countless other universes with different properties also exist, but do not support observers. Others interpret the fine-tuning as evidence for a guiding intelligence or a deeper underlying principle of physics yet to be discovered. Critics argue that the anthropic principle is not a scientific explanation, but rather a statement about selection bias. It does not provide testable predictions or mechanisms explaining why the constants are what they are. Despite this, the principle remains an important concept in cosmology and theoretical physics, influencing discussions about the fundamental nature of the universe and our place within it. 36. Grand Unified Theories, GUTS, and Theory of Everything, TOE. Grand Unified Theories, GUTS, and the Theory of Everything, TOE, represent the ultimate goals of theoretical physics: to unify all known forces and describe the fundamental nature of the universe in a single, coherent framework. Currently, physics is divided into two major pillars: quantum mechanics, which governs the microscopic world of particles, and general relativity, which describes gravity and the structure of spacetime. However, these two theories are fundamentally incompatible, leading physicists to seek a deeper unifying theory. Grand unified theories, GUTS, attempt to merge the three fundamental forces of the Standard Model: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single theoretical framework. GUTS propose that at extremely high energies, such as those present in the early universe, these forces were unified into a single force. As the universe cooled, they separated into the distinct forces we observe today. Some of the leading GUT candidates include SU5, SO10, and Padi-Salam models, which predict new particles and interactions beyond the Standard Model. However, experimental evidence for GUTS remains elusive, as proton decay, a key predicted phenomenon, has not yet been observed. The theory of everything, TUI, goes a step further by incorporating gravity into the unification, something that GUTS do not address. A successful TOE would unify all four fundamental forces, including general relativity, into a single mathematical framework. Some of the leading candidates for a TOE include string theory and loop quantum gravity, both of which attempt to describe spacetime and particles at the quantum level. Despite decades of research, no GUT or TOE has been experimentally confirmed. While they offer elegant mathematical solutions, testing them requires energy levels far beyond what current particle accelerators can achieve. If a TOE is ever discovered, it would revolutionize physics, offering a fundamental explanation for everything from subatomic particles to the evolution of the cosmos. 37. E8. Lie group theory in physics. The E8 Lie group is a highly complex mathematical structure that has been explored as a potential framework for unifying fundamental forces in physics. Lie groups describe symmetries in mathematical and physical systems, and E8 is one of the most intricate and exceptional Lie groups, containing 248 dimensions of symmetry. The beauty and complexity of E8 have led some physicists to propose that it could serve as the foundation for a theory of everything, 2E, that unites gravity, electromagnetism, and nuclear forces. One of the most well-known attempts to use E8 in physics was Garrett Lisi's exceptionally simple theory of everything, proposed in 2007. Lisi suggested that all fundamental particles and forces, including gravity, could be mapped onto the geometric structure of E8, with its various symmetry operations corresponding to different particle properties. According to this theory, new undiscovered particles should exist to fill in gaps within the E8 structure, much like the periodic table predicted missing elements before they were found. However, this idea has not yet gained mainstream acceptance, as it lacks experimental confirmation and does not fully incorporate the principles of quantum mechanics. Beyond Lisi's proposal, the E8 structure also appears in superstring theory and M theory, where it plays a role in higher dimensional unification models. In particular, heterotic string theory incorporates EAX-E8 symmetry as part of its fundamental formulation, suggesting that extra dimensions compactified into specific shapes could give rise to the Standard Model of particle physics. While E8 remains a fascinating area of research, its connection to real-world physics is still speculative. Whether it provides the key to unification or is merely a mathematical curiosity is yet to be determined. However, its rich symmetry and deep mathematical structure continue to inspire physicists searching for a more fundamental description of reality. 38. Hypercomputers and physical limits of computation. Hypercomputers are hypothetical computing systems that go beyond the capabilities of traditional Turing machines, which form the basis of modern computers. In classical computation, the Church-Turing thesis states that any computable problem can be solved by a Turing machine given enough time and resources. However, hypercomputing proposes that there are physical processes capable of solving problems that Turing machines cannot, potentially allowing for the computation of undecidable problems, infinite precision calculations, or even instantaneous solutions to complex equations. One of the most well-known types of hypercomputers is the Oracle machine, which is a theoretical device that can instantly solve problems that are otherwise non-computable by standard algorithms. Other models include supertask computers, which perform an infinite number of calculations in a finite time, and quantum hypercomputers, which leverage quantum mechanics to solve problems that classical computers cannot. Some theories suggest that black holes or certain quantum systems could act as hypercomputers, storing and processing vast amounts of information in ways that surpass conventional limits. The physical limits of computation are an active area of research in both theoretical physics and computer science. While classical and quantum computers are bound by principles such as the speed of light, thermodynamic laws, and Landauer's limit, which defines the minimum energy required for computation, hypercomputing challenges these boundaries. Some speculative theories even suggest that if the fabric of space-time itself encodes information, then the universe may function as a natural hypercomputer. Despite its potential, hypercomputing remains largely theoretical, with no experimental evidence to suggest that real-world physics allows for computation beyond the Turing limit. However, as quantum computing advances and our understanding of exotic physical systems grows, the possibility of new computing paradigms continues to push the boundaries of what we consider computable. 39. Time travel paradoxes. Time travel paradoxes arise from the logical inconsistencies that occur when one attempts to move backward or forward in time while altering past events. In theoretical physics, time travel is permitted in certain solutions to Einstein's general relativity equations, such as through closed time-like curves, CTCs, wormholes, or the warping of spacetime. However, paradoxes emerge when these time-traveling scenarios allow for changes that contradict established events. One of the most famous paradoxes is the grandfather paradox, which suggests that if a person were to travel back in time and prevent their grandfather from meeting their grandmother, they would never be born. If they were never born, they could not have traveled back in time in the first place, leading to an inconsistency. Variations of this paradox include preventing historical events, altering the outcome of wars, or creating contradictions in personal identity. A potential resolution to these paradoxes is the Novikov self-consistency principle, which states that events in a time loop must be self-consistent, meaning that anything a time traveler does in the past must have already happened in a way that preserves the timeline. This would imply that even if one attempted to change history, their actions would always lead to the same inevitable outcome. Another solution is the many worlds interpretation from quantum mechanics, which suggests that altering the past would create a branching timeline rather than a paradox, effectively placing the traveler in an alternate reality. Although time travel remains purely theoretical, scientists continue to explore its implications through quantum mechanics and general relativity. The discovery of exotic matter, traversable wormholes, or quantum teleportation effects could provide deeper insights into whether time travel is physically possible, or if the universe enforces consistency laws that prevent paradoxes from occurring.